Hi Year 12. This is our second topic in Extension 1, Year 12 Mathematics, and it's called vectors. If you're doing physics, you may find there's a little bit of an overlap with our vectors. Otherwise, you would not probably have seen them, maybe in engineering, but other than that, you won't have seen them anywhere else at school so far and have thought of them as vectors. So a vector, I'm just going to go through the list basically. So a vector is a quantity with both magnitude and direction. And what you can see over here to the right is we've got AB with a little line over the top. We would call that vector AB. Another way we might denote a vector is with a letter A or a V, and we might have a little curly line under it or over it. Or in this case, A could also be a vector. So we're going to see different ways which we define vectors soon. We have these things called scalars. A quantity that has a magnitude but no direction is denoted by mu, which is that symbol there, or lambda. And those are scalars. They're just values that we add in front of our vector, and that increases or decreases our size of that vector. We have column vectors that we denote in this way, like an A and a B. We will use those, and we'll look at those later on, so I'm not going to go into detail about those now. We're going to have a look at component vectors, where that column vector is expressed in terms of AI, BJ, where I is a unit vector in the X direction and J is 1 in the Y direction. So our A relates to X and our B relates to Y. And we'll have a look at those in the next few lessons as well. We will have a look at a displacement and position vectors. So displacement vectors are a vector that represents the displacement between 2 points shown on the number plane, and we'd write that as AB, like we saw above. So those could be any 2 points on the number plane, and that differs from our position vector, a vector that starts at the origin and denoted by the point 0, as in 0, 0, and going to some other point A would be called our position vector, OA. Equal vectors. Vectors are equal if they have the same magnitude and are going in the same direction. We have a thing called the unit vector, which has a magnitude 1. It's written like this. We're going to work it out soon, and we'll talk a little bit more about that as we go through. So there's some of the names and some of the language that we're going to have a look at, and you can look back on that as required as we go through the topic. Okay, the first thing we're going to have a look at is identifying vectors. We're not going to be working through the Cambridge textbook to start with this. We're going to be working through Maths in Focus. I think because a lot of us don't do physics in the class, we need to, I think, just work a little bit slower and have it starting off quite simply. Okay, so this first thing says, state whether each quantity is a scalar, a vector, or neither. Remembering what scalar meant, okay, so scalar is a quantity that has magnitude but no direction, and a vector is a quantity that has both magnitude and direction. So a mass of 20 kilos has a quantity, but it doesn't have a direction, so that would be a scalar. I've just popped an S there. A town 50 kilometers north gives us a direction, and that would be a vector. If we're just traveling northeast, we don't have any destination that we're going, so that would be neither. A time of 20 seconds doesn't have a direction, but it has a value, so that would be a scalar. A distance of 0 is actually a vector, because we could have a 0 vector. And due west doesn't give us anywhere we're going, so it would be neither. So we will look at these sorts of things in detail, so don't stress too much if that's not making too much sense at this point. Now, I like to think of this when we're first introducing vectors, because believe it or not, since year 9, you've actually been drawing vectors without actually knowing it. So if I said for you to draw a vector that shows a train traveling 150 kilometers on a bearing of 210 degrees, you could do that, couldn't you? You'd draw your northeast, south, and west, and you know that's a true bearing, so you'd go around and you'd draw me a line, and you'd most probably pop an arrow on it and pop 150 in there. That's a vector. You just don't know it. You haven't thought of it like that, but you actually know how to draw simple vectors. And the same with part B. A person walking 3.5 kilometers due east, it's got a value and a destination, so that would be a vector as well. It's got to have the arrow on the end. So you've been drawing them. We're just going to complicate it a little bit more for you and look at these in a little bit more detail. So let's look at how we are supposed to draw a vector. So a vector is represented by an arrow, okay? The arrow has a tip, the arrow has a tail. And that's really important. So let's write that on there. Okay, so the tip's this pointy bit up here, and the tail's the other end. Think of an actual arrow. If you were to shoot an arrow, the tip of the arrow is the bit that sticks in, whatever it hits. That's the pointy part. That's the tip, that's the tail. So this vector, we read from tail to tip, okay? So we're starting at the tail end, and we're going to the tip end. So we would call this vector AB. We're not calling it BA. We have to call it AB. Okay, so let's have a look at these vectors down below. So in this case, we're going to read the first vector N, M. I'm going to write it like that, okay? The second vector, we're going to just call V, because we don't have any other details about that vector. Sometimes when we write our vectors V, we might pop a little hat above it. We might pop a little line below it as well. So they're different variations that we could call that vector. Okay, so there's some special vectors we want to have a look at below. Okay, the first one is equal vectors. Just might highlight these for you as well. Okay, so this is sensible. If they go in the same direction and they have the same size, they're equal. Okay, so the vectors over here are all the same size. They've got the same direction. If we were to pop a north, east, south, and west plane on each of those, they would be the same direction. But they don't have to be overlapping each other. Okay, so we're just looking at magnitude and direction. We have negative vectors. Okay, so they're the same size vectors. You can see these two up here. The same angle, but they're headed in different directions. So this would be a positive. This one's going the other way. This would be a negative version of this vector, but we'll look at that soon as well. We can have zero vectors. They don't have any length, and they don't have any direction. So in this case, it's just a dot. Parallel vectors. Okay, so parallel vectors, these guys up here are parallel. They're equal as well. But these ones up here have the same direction, and they're parallel, but they might be a different size. So they're not equal, but they are still parallel. So A and B and C, same direction. Let's just find this one's a bit shorter. C's a lot longer, B's in the middle. So that sort of thing can happen with vectors as well. Okay, let's have a look at the example here. So thinking about all those points we looked at just up above there, it says in the grid of regularly spaced parallel lines, which vector is equal to A? Okay, so if it's equal, it needs to be the same direction. It needs to be exactly the same size. So that would be vector D. Vector D is equal to A. So we could write that as A is equal to D. Which vector is the negative of A? So A and B are the same size. They look like they're probably parallel, but they're going in a different direction. So the vector that's negative of A is vector B. So we could say that vector A is equal to negative vector B. And that pretty much will be enough to get you through the first part in 301. Today we want to have a look at adding and subtracting vectors as well, which is where we're heading and what we want to do. Okay, so we've got two vectors here. We've got a vector U and a vector V. And what we're going to have a look at is first of all, the triangular law of addition. So when we add vectors, we want to pop the vector, when we're adding them, from, let's have a look at what we want to do. We want to do U plus V. So if I was to put vector U plus vector V into a visual format, I would get my U vector first and I would pop it down in the same direction. And then where I have my tip of my U vector, I would put the tail of my V vector and pop that up there. And there's my U and my V. So to then find the addition of those, I'm going from the tail of my first vector to the tip of my second vector and creating a new vector, and that is called vector U plus V, and that's the addition of those vectors. Very nice, simple way, and the fact that we've actually just like picked this vector up and popped it there and popped this one over here, we can do because our vectors can shuffle around, but it's got the same direction, it's got the same size, and we haven't changed anything. That's the triangular law of addition. Okay, if you're doing physics, that's probably the way you're most likely to do your vectors there. That's the way I particularly like to do my vectors, but I need to show you the parallelogram law of addition as well. Okay, so in the parallelogram law of addition, we're going to get the same answer as we got above, okay? But what we do is we make a parallelogram out of our two vectors. So we've got vector U and vector V, and we've popped them tails together. I repeat my vector U on the other side. Okay, so it's going to be just shuffled over and starting at the tip of my vector v, and my vector v then makes a parallelogram along the top. So we've got the two vectors going tail to tail, and then we've got our two vectors over here going tip to tip. So the addition method there would be going from the tail to the tip section, and that would be the diagonal of that parallelogram, and that would represent u plus v. And if you can see, if we get rid of this bottom section and just look at the top over there, that's the same as what we've got up here anyway. So they're the two ways that we can think of when we're adding. So tails to tips still. We're always going tails to tips when we're adding our vectors. Okay, now that was a nice simple one. Let's look at what we could do if we are going to be looking at adding and subtracting these two vectors down below. So it says rearrange the vectors into a parallelogram to find a plus b and then a minus b. We might do it both ways actually. So let's first of all look at doing it with the triangulation method. The triangular method. Okay. So in that case, a plus b, I'd have my vector a, which is there. And then when I'm using the triangulation method, I'm getting my b vector and starting at the tip of my a and drawing that vector there. So my addition of a plus b goes from tail to tip. So that would be a plus b. If I was doing that with the parallelogram method, oops. Okay, I'm going to get my vector a. Okay, put him over there. That's my a. I'm going to pop in my vector b over here. Okay, now I need to pop in my other vector a and my other vector b. So I'm going from tail to tail. So I'm going to pop b over there. And I'm going across so my tips join over here. So that's my vector a. So the addition method here, I'm going from the tails to the tips. So my addition there is my a plus my b. Now that's the addition. Let's have a look at what happens when we subtract and look at vector a minus vector b. Now to work out a minus b, what I like to think of that as is a plus minus b. And that's really important because what that means is what we're doing is we're adding our a to a negative b vector. Now we looked at before previously that if that's our b vector, then our negative b vector is exactly the same direction, exactly the same size, but going the other way. So that's my minus b vector. So that's the one I want to add to my a. So if I'm going to use my triangulation method, I've got vector a here, down there, noting that I'm doing a plus minus b. So there's vector a, and I need to add to that minus b. Minus b is going to be this vector over here, so it has to go to the tip of a, and he's going to go up here like this. That's my minus b. So the addition of those has to be from here, the tail, to the tip. So that would be a minus b. Mine's a little bit out of whack in terms of size, but we can see what's happening there. Now if we look at the parallelogram method, let's draw our a vector in. So our a vector is over here. Okay. And we want to pop in our b vector, or our minus b vector. Okay. Just drawing in both of my a vectors, okay, which is similar to what I did over here, but where my b vectors went down, my minus b vectors are going up. So they're going to need to go from here to here. That's minus b. So I'm going to have to get that a little bit sorted out. And from there to there, that's also minus b. Now, we know that when we look at adding using the parallelogram method, we need to go from the tail to the tip. So where my tails are over here, and where my tips are over here, which are not joined very well. I'll fix that up a little bit. So I need to go and put that across there, and that is my a plus my minus b. If you have a look at that, that is exactly the same method as we have over here. So that's our 2 ways we could have a look at that question. Okay, let's have a look back over here. It says, in the grid of regularly spaced parallel lines, we're going to call vector OA A. So note, OA is a vector that starts at the origin, okay? And OB is called B. So we've got 2 names for that. And G over here is the midpoint of AF. Find an expression in terms of A and B for each one of these here. Okay, so let's see what we can do. So we've got CD. So CD is the vector that's going from C over here to D. That's vector CD. Now, our grid here, we've been told that the grid is of regularly spaced parallel lines. So we know that the distance from C to halfway between CD is the same as we've got down here between O and A. So we know that this distance here is A amount, and this other distance here is A amount. So we know CD is 2A. And we need to put the vector sign in there because it's 2 times vector A would give us vector CD, and so 2 is our scalar. We now want to have a look at DC. Well, DC is the vector going the other way, starting at D and ending at C. We know that vector is of size 2A, but it's in the opposite direction to OA, so it's going to be minus 2 lots of vector A. So those ones are fairly straightforward. Let's now have a look at BE. Okay, vector BE is starting at B and going all the way up there in that direction. I've just fixed up vector B, the E there, to make that look a little bit straighter. Now, if we think about what that is, that vector looks like an addition vector, okay, because it's an addition of something in this direction and something in this direction. So let's put in what we think it's made of. So remember, if we looked at the triangulation method, when we added 2 vectors, and one was from tail to tip, and we popped our next one from the tip of our first one and moved it up there, and our addition vector went from the tail to the tip of the other one. So if that was A and that was B, we'd have A plus B. That's what's happening here for us. Okay, what we've got though is a vector that goes from B to H. Okay, so we've got vector BH. Okay, and we've got vector HE. And if we were to add those, because they're going from tail to tip, we would get vector BE. So that's what we've got for vector BE, but it wants us to do that in terms of A and B. So BH, okay, along here, we're going to do it the same way as we did CD, is 1, 2, 3 lots of vector A, or 3 vector A's. HE is in the same direction as our vector B, and we've got 2 of them. So that's 2 lots of vector B. So that's a way that we can write our vector BE. It's 3 vector A's plus 2 vector B's. Okay, let's look at OG. OG. Let's get a new colour. This one's a little bit harder. Okay, OG is going to meet halfway because we've got that point there, we're up there. Let's remind ourselves what G was. G is the midpoint of A and F. So what we've got happening there is we've got half a vector B there and half a vector B there. And half a vector B and half a vector B make a whole vector B, and that's what our AF is. But we want to have OG. So if we think again that OG is an addition vector, and that's made up of this vector along here called OA, plus our vector up here, AG, that gives us OG. So I'll write that out down here. So OA plus AG is equal to OG. Now let's think of that in terms of addition. What have we got? We've got OA being vector A and AG being half of vector B. So we've got vector A plus half of vector B, and that's my OG. We're nearly there. We now need EG. Okay, so EG goes in the other direction. Oops, I'll just fix that up. Okay, so EG is going the other way. Okay, we're looking at, generally our vector's going this way, we're going the other way. So maybe it's a negative vector. We need to have a think about how we could get that as our vector. So have a little think. It's just a matter of thinking, well, if thinking of that as my addition vector, let's see if we can move vectors around to get that. I'm looking at that and thinking, well, if I started here and I had this one across here and this one down here, that would get me my EG. So we know this vector here, let's call that J. I'm going to pop a J in there. Okay, so we know what that is because that's the same. EJ is the same as DC. So EJ is minus 2A. JG. What do we know about that? Well, we know that this distance from G to F, we said was a half of B, vector B. And we know that we've got this vector here being of size B, and we've got two of those. So we've got 2B, and we've got a half of B. So we've got two lots of B plus half of B. We've got 2.5 B, and that's going to be, though, in the negative direction to our vector B. So we've got minus 2.5b, and that's from J down to G, and that's a negative vector, which should be what we've got there, so minus 2.5b. So our vector EJ is minus 2a, and our vector JG is 2.5b, which I think I might write that as 5 over 2. And that's our answer. And one lucky last tip here, it's just saying a shortcut method. It says when vectors join tip to tail, such as vector AB plus BC plus CD, we can just cross off the middle letters such that we get A going to D and make one huge vector. Because they all would be joined, so they would all be in a line and all be parallel, so that would work out. So if we had, for example, OV plus VP plus PQ, they're joining, okay, the letters, so we could call that vector OQ. In this case, if we've got A to B minus C to B plus C to A, if we're crossing off those middle terms, we've got A to A, which is just the 0 vector in that case. And there are our notes.